Dear colleagues, good day, and welcome to the Moscow Telecommunications Seminar. Our today's speaker is Roman Zlobin. Roman received the bachelor degree in applied mathematics and physics from the Moscow Institute of Physics and Technology in 2022, and he is currently pursuing master's degree. He is currently a junior researcher at the Wireless Network Labs of ITP, and his research interests includes Uplink NOMA, Wi-Fi, and prototyping of wireless devices. The topic of the talk of Roman is prototyping and experimental study of Uplink NOMA in Wi-Fi networks. Roman, the floor is yours, so please.
Thank you. Hello, everyone. I'm very happy to see you all on my talk. And today I will speak about prototyping and experimental study of uplink non-orthogonal multiple access in Wi-Fi networks. Before I continue, if you have any questions, I will gladly try to answer them after my presentation. So let's begin. Wi-Fi is one of the most popular technologies for wireless internet access. Developed in 1997 by the Institute of Electrical and Electronics Engineers IEEE as an 802.11 standard. Wi-Fi is constantly evolving, and a new amendment to the IEEE 802.11ax standard allows for a maximum throughput of up to 10 gigabits per second. That is significantly improving the quality of user service. The upcoming addition to IEEE 802.11be, also referred to as Wi-Fi 7, aims to achieve up to 40 gigabits per second throughput. Throughput increase in heterogeneous Wi-Fi environments is one of the main goals for the IEEE 802.11 working group. The increase in throughput is mainly achieved by increasing the width of the frequency channel for transmission, the use of higher orders of modulation coding schemes, as well as the use of MIMO technology. In addition to these approaches, new data transmission methods are needed for future Wi-Fi networks to increase throughput and support dense deployments. Wi-Fi networks often consist of devices from different generations, so these methods need to support backward compatibility. And uplink power domain non-orthogonal multiple access, or uplink NOMA, is one of the promising methods to address this problem. There are many research demonstrating the effectiveness of using uplink NOMA in another popular wireless communication technology, fifth generation cellular networks. Consider the common methods of multiple access. They are shown on the slide. When using time division multiple access, or TDMA, data from only one device can be transmitted simultaneously in one frequency channel. In frequency division multiple access, or FDMA, data from different users can be transmitted independently and in several different frequency channels. Orthogonal frequency division multiple access, or FDMA, is a combination of these two access methods, where time frequency resources are divided into parts that can be defined for different users. However, when using these access methods, data from only one user can be transmitted in one time frequency resource. Otherwise, a collision will occur. When using non-orthogonal multiple access on NOMA, multiple users can transmit data on the same frequency at the same time. This report will talk about power domain NOMA. And in this case, NOMA increases the spectral efficiency of wireless networks by separating signals by power. To transmit and receive signals by using NOMA, it is enough to have only one antenna on the transmitter and receiver, unlike multi-user MIMO technology. As I said, in my presentation, attention is paid only to power domain NOMA. However, there are other NOMA solutions. Unlike power domain NOMA, which attains multiplexing in power domain, code domain NOMA achieves multiplexing in code domain. There exist some other multiple access technologies which are also closely related to NOMA, including pattern division multiple access or PDMA and spatial division multiple access. The plan of my talk will be as follows. Firstly, I will tell you general information about power domain NOMA. Then, how Uplink NOMA can be used in cellular networks. And the main part will be devoted to the use of Uplink NOMA in Wi-Fi networks. I will describe how NOMA is used in a downlink channel. There is one transmitter that can be access point or base station, and several receivers related to users with different channel conditions. In the case of downlink, data is sent from one transmitter to several receivers at once. Let's look at the example of two users. The power coefficients for the user data in the NOMA signal are divided as follows. Most of the power is allocated to the signal for the user with the worst channel conditions with a stronger attenuation. Further, a signal for the near user is embedded inside the signal of the far user. The generated NOMA frame is sent from the transmitter, passes through different channels to the users. For a distant user, the embedded signal is perceived as noise, and he simply decodes his data. Thus, the farthest user may not even support NOMA technology, since for him, such a transmission is no different from the usual one. After receiving the NOMA frame, the near user first decodes a higher power signal intended for the near user, treating the embedded signal as noise. Next, the signal for the distant user is subtracted from the general signal to highlight the nested signal intended for him. This process is called successive interference cancellation. NOMA transmission is not limited to two users. In case of large number of users, the signals are similarly embedded into each other as the channel conditions of different users improve. At the same time, the nearest user, when receiving frames, sequentially decodes and subtracts signals intended for all other users. Since the signal in the case of downlink is transmitted by a single device, signal modifications can be used for this. For example, symmetric superposition coding or rotation of cancellations inside the NOMA frame. My colleagues from the lab worked on the implementation of downlink NOMA in Wi-Fi networks. The created prototype of the downlink NOMA supported backward compatibility, so a distant user could be a legacy device of the 802.11a standard. And more detailed information can be obtained by watching Alexei Kureyev's seminar on downlink NOMA in Wi-Fi. Now, let's move on the uplink case. In case of downlink, transmitter can choose whether to use multi-user MIMO technology or NOMA. But in uplink, NOMA and multi-user MIMO can be used together. Multiple antennas on the transmitter allows focusing the beam on the receiver, while NOMA is used for a signal division for multiple users. Now the situation is reversed. Several users simultaneously transmit the data to one receiver. Signals from different users are multiplexed in a physical channel, and a superposition of these signals comes to the receiver. Due to different channel conditions, frames from users, when received, have different signal power. Next, the receiver uses SIC, successive interference cancellation, to sequentially decode frames from all the users. The difficulty of NOMA transmission in uplink is that signals from different users must be synchronized in time and frequency. Also, the receiver must determine the channel conditions for each individual user. In case of downlink, there were no such problems since the transmission acquired from a single device. More details about this will be dealt with further. Now, I will tell you how Uplink NOMA is used in cellular networks. One of the main features of cellular networks is centralized management of the base station. Time frequency resources are distributed between different physical channels. If we talk about grant-based NOMA in uplink, then the transmission from the user equipment to base station occurs according to a schedule. When connected to the network, user equipment is synchronized in time and frequency using synchronization signals transmitted by the base station. There is also a timing advance for user equipment to align slot boundaries in uplink transmission. Also, user equipment transmits sounding signals so that the base station can assess uplink channel state information. The major difference between OMA and scheduling-based NOMA is that the latter allows multiple superimposed transmissions on the same radio resources, while the former only allows orthogonal transmissions. Hence, the resource allocation and demodulation reference signals should be designed to facilitate scheduling-based NOMA. Also, having precise synchronization in time and frequency enables to use more complex cancellation configurations. For example, cancellation rotation, as it's possible in downlink NOMA. The major drawback of the scheduling-based NOMA is that the signaling overhead occupies a large portion of radio resources, which makes the grant-free NOMA inevitable. On the slide, you can see a comparison of the signal procedures between the scheduling-based transmission in LTE and the grant-free transmission. User connection occurs according to random access procedure. After that, a scheduling request is transmitted to the base station if the buffer is not empty. And the user doesn't transmit packets until it receives the uplink grant from the base station. The above mentioned procedures may take dozens of milliseconds, which impose large signaling overhead. Also, it consumes more power for the signaling transmission or detection, and incur large latency for the data transmission. In contrast, grant-free NOMA can significantly reduce the signaling overhead. Due to decentralized uplink instant transmissions, the signals of users are multiplexed, which naturally leads to non-orthogonal transmissions. It is agreed that grant-free NOMA is more suitable for massive machine-time communication scenario due to the following concerns: energy saving, low-cost devices, and latency and signaling overhead reduction. According to where the random access channel is required, grant-free transmission can be classified into random access channel based and random access channel less grant-free. In order to reduce the signaling overhead, the random access channel procedure could also be cancelled. However, the absence of random access channel may result in the asynchronization among users, which may cause large detection complexity at the receiver. After discussing how Uplink NOMA is used in cellular networks, let's move on to how this technology can be used in Wi-Fi. In this chapter, I will talk about the organization of Uplink NOMA transmissions and the frame format, both for compatibility with legacy 802.11a standard and for new Wi-Fi standards. I will also tell you about frame processing and an experimental study of Uplink NOMA in Wi-Fi. The main difference between Wi-Fi networks and cellular networks is the use of the method of random access to the channel. Also, Wi-Fi devices are usually cheaper than cellular networks, which may impose some restrictions on the complexity of signal processing procedures. Also, the characteristic distance at which Wi-Fi networks operate is less than for cellular networks. So the difference in signal power from users varies within smaller limits. Therefore, transmission between only two stations and one access point is preferable at once. First, let's introduce the terminology. Consider a Wi-Fi network consisting of one access point and two stations located at different distances from access point. The primary station is located further from the access point and accordingly has the worst channel conditions. The nearest station will be called secondary station. These stations simultaneously in the same frequency channel send primary and secondary frames, respectively. These frames are multiplexed in the physical channel, forming a NOMA frame. In it, the signal of the secondary frame has more power than the primary one. When access point receives a NOMA frame, it first processes the secondary frame, then subtracts it from the total signal, and processes the primary frame. Further, in the case of backward compatibility with the legacy 802.11 standard, as well as with the modern 802.11ax standard, they will be considered separately. In the legacy case, the primary station is a device operating according to the 802.11a standard. So the frame format and transmission methods for it remain unmodified. Let's move on to organizing the transmission of frames in the network. To support backward compatibility, it is proposed to use transmission with request to send and clear to send frames, or RTS-CTS. Let one remote primary station in the network initiate transmission with an RTS frame. Secondary stations, if they want to participate in uplink NOMA transmission together with this primary station, immediately after RTS, send reservation signals. These signals must be orthogonal to each other for different secondary stations. They can be special short waveforms or time sequences, since the access point must process them for short interframe space between RTS and CTS. Having received the RTS frame and several reservation signals, and having determined power of different signals, the access point decides which of the secondary stations should participate in the uplink NOMA transmission together with the primary station. After that, it sends back the CTS frame and the specific reservation signal. Then the uplink NOMA transmission takes place, and at the end of it, the access point can send an acknowledgement frame using downlink NOMA. This method of transmission is described in more detail and studied in the article by my colleagues. If we talk about modern Wi-Fi standards, then the 802.11ax standard has trigger frames that are used to organize multi-user OFDMA and multi-user MIMO transmission in uplink. The same frames can be also used to initiate uplink NOMA transmission. Also, an important factor when transmitted to uplink NOMA is the frequency and time synchronization of signals from different stations. This synchronization can be performed by receiving RTS-CTS frames or trigger frames. Now we turn to the formats of frames at the physical level and their processing. The slide shows primary and secondary frames. To decode the primary and secondary frames, the access point has to estimate the channel from each STA and perform phase correction using pilot subcarriers. With the original legacy frame format, the preamble and the pilots of the low power on the receiver primary frame overlap with those of the high power secondary frame. So it is impossible to estimate the channel accurately and perform phase correction for both frames if we use unmodified frame structures. We proposed the secondary frame format that solves these issues, while format of the primary frame remains legacy. The preamble of the legacy Wi-Fi frame consists of the short training field, the long training field, and the signal field. LSTF is used for packet detection, power estimation, and frequency offset correction. LTF is required for fine time and frequency synchronization and channel estimation. And LSEG contains information about modulation encoding schemes, MCS, that is used for the rest of the frame, and the length of the frame. LTF contains two identical sequences, LTF1 and LTF2, and a double guard interval of 1.6 microseconds. The proposed LTF field format of the secondary frame allows the receiver to extract the channel state information for both primary and secondary frames. It is divided in two parts, each having a guard interval of 0.8 microseconds. The first part contains a phase inversed LTF1 sequence, and to simplify channel equalization, the signal of the on each subcarrier in the LTF1 of the secondary frame is multiplied by additional phase, where F is carrier and carrier and subcarrier frequency difference. That is equals 4 microseconds. That is duration between LTF1 and LTF2, and equals the duration of one FDM symbol. And the second part of LTF contains an unchanged LTF2 sequence. These modifications make it possible to estimate channels independently for primary and secondary frame. Similarly, in the case of the 802.11ax standard, high efficiency LTF sequences, or HE-LTF, can be used to estimate a channel, which are also used to estimate channel in multi-user MIMO. Also, it can be used to estimate channel in Uplink NOMA, and the required number of them can be set to evaluate channel when transmitting frames from two stations in Uplink NOMA. It is necessary to use two HE-LTF. Because of the overlap of pilot subcarriers in OFDM symbols, it is impossible to adjust the phase separately for each frame. This is important because the phase in the signals may change due to some deviations in frequency synchronization or due to channel changes during transmission. Therefore, we apply pilot puncturing of the secondary frame for every odd OFDM symbol, starting from the first one in LSEG. Thus, we get pilots for the primary frame in these OFDM symbols and correct its phase. Then we subtract the obtained pilots from the even OFDM symbols and correct the phase of the secondary frame. For 802.11ax frames, half of the pilot subcarriers can be transmitted in each OFDM symbol to avoid their overlap with the pilot subcarriers of another frame, as shown on the slide. When receiving a NOMA frame, the access point must first process a secondary frame of higher power, then subtracting it from the total signal, proceed to processing the primary frame. Consider the two interference cancellation schemes. On the slide, you can see scheme of classical successive interference cancellation, or SIC, on the receiver. Firstly, the signal of the secondary frame is processed and decoded Then the received bytes are restored to a signal in frequency domain and subtracted from the NOMA frame. Thus, the receiver processes the frames sequentially. Another method is parallel cancellation demapping, or PCD. The higher power signal of the secondary frame is initially determined using a hard bit demapping and subtracted from the NOMA frame. Thus, the lower power primary frame signal is fast extracted. Then, the receiver processes both frames in parallel. PCD is faster compared to SAC, which is important since after the reception of the data frame, it is necessary to send an acknowledgement frame through the sieves interval of 16 microseconds immediately after data frame reception. This problem for the SAC can be solved, for example, by generating an acknowledgement frame in advance. However, the SIC method is more noise resistant and expands the range of signal powers for uplink NOMA transmission, what will be seen next. To analyze the effectiveness of the proposed methods, we made an experimental testbed. Our testbed consists of two software-defined radios, USRPs, and to reproduce the simultaneous transmission of two frames in uplink NOMA, the first USRP with two independent takes outputs is used. The transmitter sends the primary and secondary frames separated by power from two different antennas. The second USRP is used as uplink NOMA receiver, and slide shows the described testbed. We use a single transmission device to produce accurate time and frequency synchronization. In addition to the usual transmission of frames for efficiency analysis, the prototype was used to transmit two video streams over UDP using uplink NOMA. Using our testbed, we evaluated the effectiveness of the proposed NOMA frame format when using PCD and SAC methods. The primary and secondary frames with a payload of 1,500 bytes and with the same duration of 700 microseconds are transmitted in uplink NOMA. MCS3 with quadrature phase shift gain or QPSK was used for primary and secondary frames. A signal to noise ratio, or SNR, was equal 11 decibels for the primary frame in single transmission. At these SNR values, frames with the described parameters were received with 100% probability in a legacy transmission. We measure a frame receive ratio, or FRR, for primary and secondary frames, varying the signal to interference and noise ratio, SINR, of the secondary frame. On the plot, you can see FRR for both frames in uplink NOMA transmission. FRR values are low for both frames, for SINR values below 0 and below 8 decibels, because the points of the signal cancellations of the primary frame fall into the wrong decision area, which leads to errors in both primary and secondary frames reception. On the picture, you can see the signal cancellations of NOMA frame and the signal of the primary frame after processing. For higher SNR values, FRR increases for both frames because there is no intersection of cancellation in this case. With the further rise of the secondary frame power, there is an FRR decrease of the primary frame because of the phase noise, which is crucial when the power ratio between secondary and primary frames is high. You can see on the picture that the signal is received with errors. For the combination of MCS3, it can be seen that the difference between PCD and SAC is insignificant. However, when using a combination of MCS3 and MCS4, it is more clearly seen that the noise immunity of the noise resistance of the SAC method is higher compared to PCD. This is due to the fact that the points of the signal constellation of the secondary frame are closer when we use 16 QIM than when we're using QPSK. For these two experiments, FRR of the primary frame doesn't exceed 1, as it was obtained for a single transmission of the primary frame. Although at SNR values equals 11 decibels for the primary frame, the FRR during a single transmission is 1. When transmitted using Uplink NOMA, the signal of the primary frame is more distorted after separation from the general signal of the NOMA frame. And because of this, FRR of the primary frame decreases. But by increasing the total power of the NOMA frame, FRR equals to 1 is achievable. Next, the network throughput using Uplink NOMA was compared to the throughput using TDMA, as described in the 802.11a standard. To compare Uplink NOMA and TDMA, a simulation model, which was calibrated according to the results of the experiment, is used. Scenarios with TDMA and Uplink NOMA is shown on the picture. In the first case, two stations transmit using TDMA only. Then there are single transmissions of the secondary stations and joint Uplink NOMA transmission. In the latter case, the transmission occurs only in Uplink NOMA, which corresponds to the proportional pair to maximize the geometric average throughput. Thus, in comparison with TDMA, when using Uplink NOMA together with a single transmission of the secondary station, the throughput of the secondary station will double. However, the throughput of the primary station will decrease by 9% because FRR is equal 0.91 for primary frames in the experiment. At the same time, the geometric mean will increase by 35%. In the case of transmission only using Uplink NOMA, the throughput of both station increases, and the geometric mean increases by 54%. I would also like to mention the possibility of connecting Uplink NOMA with other technologies used or gaining popularity for wireless networks. Several users in NOMA can transmit not over the entire channel, but in separate resource units, which will make resource allocation even more flexible compared to FDMA in Wi-Fi. There are research demonstrating the advantages of using multi-user MIMO together with NOMA schemes compared to multi-user MIMO schemes. As mentioned, several antennas can be used to amplify the signal using beamforming, and further use NOMA to separate the signals in NOMA frame. Reconfigurable intelligent surfaces or RIS are popular research direction now. They are usually used to amplify the signal on the receiver by changing the conditions in the channel. RIS perfectly fits with NOMA idea by focusing the transmitter beam in the direction of multiple users and serving them in one beam. Let's move on to the conclusion. Although SAC shows better results compared to PCD when receiving NOMA frames, it requires more computational complexity. And it is also necessary to reduce frame processing delays. An increase in throughput compared to TDMA has been demonstrated in the case of backward compatibility with legacy device. However, in order to prove the feasibility of using Uplink NOMA in Wi-Fi, it is necessary to conduct a wide experiment comparing Uplink NOMA technology and FDMA, which is now used in 802.11ax standard. It was also shown that the implementation of trigger-based Uplink NOMA doesn't require a large number of modifications, which is good for the possibility of standardization of the technology in future Wi-Fi standards. That's the end of my talk. Thank you for listening. And now, if you have any questions, I will gladly try to answer them.
Thank you, Roman, for the interesting talk. We have one question in the chat. Could you read it by yourself?
Yes. Slide 14. Is there any technical difference between Uplink NOMA with trigger frames and Uplink multi-user MIMO? At the first glance, the processes seem identical. About this question, it's true that for multi-user MIMO and Uplink NOMA, it is quite a similar procedure while transmitting frames in Uplink, and the differences would be in the frame processing procedure, because we use only one antenna, for example, only one antenna on the receiver and transmitter, and we should use SAC to decode both frames. But as I said, the modifications of trigger-based NOMA in 802.11ax standard is less than for 802.11a standard, so they are pretty similar.
Ilya, are you okay with the answer?
Yes, thank you for your answer. I was also wondering about the following fact. You just mentioned that SIC can be used when the receiver, the access point, has one antenna, yes?
In Uplink NOMA, yes.
Yes, but would there be any significant differences if access point has at least two antennas?
I think that there is no significant differences because if we use several antennas on the receiver for the Uplink NOMA reception, we could make just make a more precise channel estimation and decoding procedure. Just averaging the signals from the different antennas.
Okay, I see. Thank you.
If we are talking on this topic, can I add something? So I think you state that the access points do not use, currently access points do not use successive interference cancellations. Is my understanding right?
They are not used successive interference cancellation for Uplink NOMA, but in multi-user MIMO technology, it can be used in MMSE SIC methods to make the interference from the different spatial streams less when receiving the frames, but not in all access points, as I know.
So the only benefit of Uplink NOMA is that you also multiplex users additionally by power, not only by antennas.
If we're talking about use MIMO for beamforming in Uplink, that's true. There is some works on other usage of sorry, maybe I wrong understand your question. Could you repeat, please?
Okay, so my question was that you connect the successive interference cancellation and NOMA, but successive interference cancellation is just a method to separate two signals, but it's not always connect to NOMA. So MU MIMO also can use SIG, right?
Yes, that's true.
Okay, that was just my comment to clarify.
Okay, thank you.
Okay, let us go to the next question in the chat from Kirill Blinsky.
What is your opinion about the performance scaling of the proposed methods for greater number of antennas supported by late releases of Wi-Fi? As I said, if we use multiple antennas, for example, on stations that transmit signals in Uplink, we could use beamforming just for increase the power and the difference in power that could increase the decrease packet loss ratio. If we talking about multiple antennas on receiver, as I answered for the question of Ilya, we could use the signals from each antenna, and we could use them to make a precise, more precise demodulation decoding. So it will increase the performance of the Uplink NOMA.
Okay, thank you. Maybe more questions from the audience by voice.
I have one more question. This is more like your opinion about possible implementation of NOMA, either uplink or downlink in the standard. So if uplink NOMA were, for example, accepted as one of the methods to be used in future 82.11 amendments, would the signaling need to be changed in the standard somehow, or we should try and keep the backward compatibility and somehow involve even the devices of prior amendments to the NOMA process?
Thank you for the question. I think, for my opinion, maybe if the if there is will be standardization of uplink NOMA, it should be two ways to use it. The first case in legacy compatibility that can because this performance would be not so big as for the connectivity with more modern devices. Because in my talk I said that legacy devices 802.11a standard, they usually have only one antenna, and it requires to receive, for example, acknowledgement frame after data transmission in time. So it brings some problems with the usage of some complex solutions that could bring a better performance. But if we're talking about new devices that from the new Wi-Fi standards, it could be possible to make some modified solutions to organize uplink NOMA transmission. Also, I mentioned that in cellular networks, if we have precise fine frequency synchronization, it could be used to some complex signals for the uplink NOMA. And for example, in this case, in case of new devices, we could make some technique that make this precise time and frequency synchronization that could make the better performance.
Okay, thank you for your perspective.
Thank you for the question.
Okay, then I have two questions. So the first question is related to modification of the physical layer frame formats. Could you please return back to the slides with the described modifications? Okay, yep. So as I understood, so first of all, the access points processing of the frame format should be modified. So again, if we need uplink NOMA, we need to modify access points. What about primary and secondary stations? If both of them need to modify their generated frame formats, or just some station needs modification?
As I mentioned, the in this case, we consider the backward compatibility with legacy devices, and the primary station is a legacy device. It's 802.11a standard. So there is no any modifications that is made for primary frame as for frame structure or as transmission schemes, and and we should modify only secondary stations and access points, as you mentioned.
Okay, so primary is backward compatible. Stations still remains backward compatible. Okay.
Yes, yes.
Okay, thank you for that. The second question is related to synchronization. So you mentioned that for proper operation of NOMA, it's very important to have a very tight synchronization of in frequency and time domain. And we know that in Wi-Fi, because of more cheap devices and because of more complex synchronization procedure, we will have synchronization errors. So the frame will arrive not exactly synchronized at the access points. So the question is, in your experiments, have you modeled these synchronization errors? And have you studied how the synchronization errors can influence the performance?
Yes, we have studied that how the frequency synchronization errors could make the reception worse. So yes, there is a problem, but if we the solution to this maybe is to synchronize to the legacy devices in the case of backward compatibility. And if we're talking about modern devices with the standard of 802.11ax, there is going to use a MIMA and FDMA in Uplink. So in these devices, there is more precise time and frequency synchronization that is made by receiving trigger frames. So Uplink NOMA in this case would work better. Also, if you're talking about time synchronization, it could be in the it should be in the cyclic prefix duration. So in this case, the Uplink NOMA works. If the asynchronization would be more than 0.8 microseconds, the reception would not be possible. But in legacy devices,
did you study about legacy devices? So, for example, if you after RTS you ask them to start frame transmission after some CIFS, what is like the difference in the start of the frames of different devices? Is it below the cyclic prefix you mentioned, or it's higher than cyclic prefixes? So what are the typical values?
We made only the frequency synchronization.
No, I'm talking about time synchronization.
We don't make the time synchronization for the legacy devices, but in standard, as I remember, there is a percent that could be an error in time synchronization between RTS, SCTS, and other frames. And this is less than 1 sector prefix, as I remember.
Okay, thank you.
Thank you for the question.
Any other questions? Then let us thank Roman for the very interesting topic and for the answers. And we are finishing our today's seminar. I would like to thank all attendants and the people who are asking the question. And thank you all. See you next time. Goodbye.
Thank you for listening and your questions. Goodbye.